Hello, welcome to Enigma, a series of videos in which I'm going to explain some of the mathematics of the World War II Enigma cipher and the various attacks on it. So in this introductory video, I'm just going to explain from a mathematical point of view a little bit about how the machine worked. So the series is aimed at people with a little bit of background in pure mathematics, but it won't assume any knowledge of the Enigma machine itself. So you'll need to know a little bit about permutations, but no more than would be covered in a first course on abstract algebra, and maybe later a little bit of statistics and probability. I'll be concentrating on the mathematics of Enigma, not the history or the engineering, but I'll try and give some references from time to time if you want to follow those up. Okay, so let's begin by going through the various functional parts of the Enigma machine one by one. And the part to start off with is the keyboard in the bottom left of the screen here. So the keyboard has 26 keys labeled A to Z, so no numbers, no symbols, no upper or lower case, no spaces. And the machine worked by encoding one letter at a time. So when you pressed a key on the keyboard, it made an electrical circuit and a signal is sent through the machine following the path which I've indicated with these arrows here. So the first thing that happens is the signal goes into the plug board or stecker board. And what that does is to swap some pairs of letters and leave some other pairs alone. So exactly which pairs it swapped over was something that you could configure. Next, after that, the machine passes into the three rotors. So each rotor acts as a permutation on the letters of the alphabet. And usually, in the most common form of the Enigma machine, there were three rotors. So the three rotors we will refer to as the right hand or the fast rotor, because it was on the right hand part of the machine, and then the middle or the medium rotor, and then the left or the slow rotor. I'll talk about why they were fast and medium and slow later on. Okay, so after they've gone through the rotors, they then enter the reflector. And what the reflector does is to swap all 26 letters in pairs. It's what mathematicians would call a fixed point free involution. So it swaps each of the 26 letters in 13 pairs and then sends the signal back in the way it came in the opposite direction. So after going through the reflector, it would then pass in the opposite direction through the slow rotor, then through the medium rotor, then through the fast rotor, then after that back through the stecker board, and finally it goes out into the lamp board. So the lamp board has 26 lamps, and one of those lamps will light up, and that is the output letter corresponding to the input letter which was typed. Okay. So we can think of each encoding part of the machine as implementing a permutation of the alphabet. And I've given some names to the permutations here. So first, the plug board permutation, the very first one to be applied, is called S. And it has a special form. So the plug board permutation is an involution. It's a product of some disjoint two cycles. So for example, let's just put the correct pen on. Get rid of that. So what might it look like? It might look like a product of two cycles. It might be something like, I don't know, T, Z, U, V times W, A. Right? If you connected together T and Z, and you connected together U and V, and you connected together W and A, then the effect of the plug board would be to swap those letters in pairs. Okay, the next three rotor permutations, so L and M and N, as I've called them, there's nothing particularly special about those. They could be any permutation. And the final one, the reflector permutation, which we've called R up here, this one is special. So this one is, as I said before, that one is a fixed point free involution, a FPF, short for fixed point free involution. So that means it swaps all 26 letters of the alphabet in 13 pairs. I'll show you an example of a real reflector permutation in a moment. Okay, So let's work out the overall permutation performed by the Enigma machine, because it's going to be a composition of some of these permutations. So the first thing that happens in the machine is that it first does the permutation S. Okay, after S, it passes through the right hand, the fast rotor, L, then it goes through the medium rotor, M, then it goes through the slow rotor, N, and then it passes through the reflector. And the reflector sends everything backwards through the rotors in the reverse order and then through the plug board or the stacker board. So since it passes through the slow rotor backwards, the effect is to do the inverse of the permutation N, and the inverse of M, then the inverse of L, and then finally the inverse of S. Now, of course, S being an involution is its own inverse, but we'll write it like this just to make clear what structure is going on, because now we can see that this is a conjugate of the reflector permutation R. Now, conjugates of permutations always have the same cycle type, so that means the overall Enigma permutation, the one we've seen here, will always be a fixed point free involution. FPF, fixed point free involution. Okay, so the Enigma permutation in any configuration of the machine is always a fixed point free involution. And that means the Enigma has two really important properties. So firstly, it never ever sends a letter to itself. So the letter M can never be encrypted to M. And secondly, it always swaps letters in pairs, so that if it sends A to X, then in the same machine state, it would also send X to A. And that means that in order to decrypt a ciphertext encoded by the Enigma, all you've got to do is put it in the exact same configuration that we use for encryption and type in the ciphertext, and the plain text, the original plain text, would then come out one letter at a time on the lamp board. Okay, so that's how the standard, the most basic three-rotor Enigma worked. Right, so let's look a little bit more at some example rotor permutations. So I'm going to look at a couple of real examples of rotor and reflector permutations. So if you look up, for example, in one of the links at the bottom of the screen there, which I will put in clickable form in the description, then they will tell you the actual permutations implemented by some of the rotors and reflectors that were actually used in the real Enigma machine. So I've written, to begin with, an example of one of the rotor permutations, the rotor that's conventionally called rotor number 1 in Roman numerals, in two-row notation to begin with. So that means the rotor sent A to E and B to K, C to M, D to F, and so on. And then in cycle form over here. Okay. So you can see that these rotor permutations didn't really have any special structure. So I mean, a good question is, what does this permutation actually mean? I mean, the thing about rotors is that they rotate, and when they rotate, it changes what permutation they do. So, like, you know, which actual permutation is this? What does it mean when you look on the Enigma, on the wiki page for Enigma rotor details, and it gives you one permutation for each rotor? So the answer to that is this is the permutation performed by the rotor when it's in one particular position, one particular configuration, which I will call the neutral position, and I will define a little bit more carefully later. Okay, so I guess there is one special thing about these rotor permutations. I said they could be anything, but there is something that's not quite right about them, which is that this one has like one fixed point here. You can see that the letter S got sent to itself and no other letter got sent to itself. Now, if you pick a permutation of 26 letters uniformly at random, then there is a roughly 2/3 chance that it will have a fixed point. But if you take the 10 real examples in the first link below, the one I'm highlighting now, you'll see that actually only 3 of them have got fixed points. And that's a very low possibility of that happening by chance. It's about 3%. So there's some kind of weak evidence there that when they were choosing how to wire up their rotors, they tended to avoid fixed points. I mean, you can sort of imagine why they wanted to Okay, so let's move on to the reflector example here. This is what was called reflector A. I've written it in 2-row notation, so that meaning of this, these 2 rows of letters is that the reflector send A to E, B to J, C to M, D to Z, and so on. And if we write it in cycle form, you can see that, as I said earlier, what you've got is a product of 13 disjoint 2 cycles. It swapped all 26 letters of the alphabet in 13 pairs. So it sent A to E and E to A, B to J and J to B, and so on. Okay, so it's a fixed point free involution, a product of 13 disjoint 2 cycles, swapped all 26 letters in 13 pairs. Okay, right, next slide, please. So here we go. We need to understand about rotors rotating, right? The whole point of a rotor is that it rotates. And each of the 3 rotors in the machine, but not the reflector, at least in the standard rotator, could rotate. These rotors were separate from the machine. You could open the machine up, take the rotors out, put them back in a different order. You could actually manually rotate them. And each rotor could rotate 1/26th of a turn at a time. So before we look at exactly when they would rotate, we need to understand the effect of a rotor rotating on the permutation it implements, and we need to understand a little bit more about the rotors themselves. So to begin with, here on the left, you've got a diagram of a side-on view of a rotor. So a front-on view of the machine, you would see the rotors side-on. So around the outside on the left here, you've got what is sometimes called the alphabet tire. So that had the letters of the alphabet equally spaced in their usual sequence, or sometimes it had numbers instead of letters. So it might have the numbers 0 to 25 instead of A to Z, and we will occasionally identify the letters A to Z with 0 to 25 when it's convenient to do so. So when you put the rotors into the machine and close the machine case, there's a little window through which you can see one and only one of the letters on the alphabet tire. And that visible letter is called the window position. So to set the window position, you could actually adjust that when the rotors were in the machine by using this bit here, which was stuck out of the machine. It had little notches that you could use with your fingers to turn the rotor around. So that bit I've just drawn a blue arrow to stuck up out of the case, and you could use it to set the window position to whatever letter you wanted. Okay, so what about these rotors? Right, the rotors had input contacts on the right and output contacts on the left, which connect electrically to the wiring carrying the signal around the machine. So you can see here that I've labeled the input and output connections. So here are the input contacts, and here are the output contacts. I've labeled them with the letters A to Z. And I've got the rotor in what I'm going to refer to as a neutral position, where the input contact label A lines up with the rotor contact A, and so on. So the meaning of this labeling is that if the rotor were in the fast position and you pressed A on the keyboard, then the signal would enter just here through the input contact labeled with the letter A. All right, so inside the rotor are wires connecting input and output contacts, which determine the permutation that it performs. So for example, there might be, I'm going to draw these wires now, there might be a wire from A to E, which means if the signal entered the rotor through its internal contact label A, then it would go out through E. And as another example, maybe B is connected to G like this. I'm going to draw the wire in again, and maybe C is connected to A like this. Okay, maybe D is connected to D, and so on. So there would be one, each input part of the rotor would be connected to an output part of the rotor to determine which permutation is performed by the rotor. So we're going to give the name M to the permutation performed by this rotor, so that M of A would be equal to, let's have a go at drawing that in a slightly more legible way, M of A will be equal to, what did I say? I said E M of B will be equal to G, right, M of C would be A, and so on. Okay, so, oops, sorry. So here's how the rotors rotate, right? When the right hand, or the fast rotor, moves 1/26 of a turn each time a key is pressed. To be precise, the rotation happens before the signal goes through the circuit, and the rotor rotates, the fast rotor rotates 1/26 of a turn toward the keyboard, toward the person using the machine. So the letter in the window increases, takes one step forwards through the alphabet. So if it was A before, as it was on my left-hand rotor here, then it would become B, as it is in the right-hand rotor that shows what the rotor looks like after one step of rotation. So it would keep doing that once each time you press a key. Okay, so you can see that now after this single rotation, actually before I talk about this, let me connect up the rotor the same way it was shown before. So B was connected to G, A would come up and be connected with E. You can't see the A contact on the rotor anymore, but it will be somewhere sort of down there. C was connected to A, so that's also going to disappear off, and D was connected to D like this, and so on. Okay, so you can see now that the external wiring and the rotor contacts are now aligned differently, so that an input of A is now connected to the B contact internally in the rotor, and an input of B is now connected to the C contact. The input of C is now connected to the D contact. So the inputs have all been shifted one up in the alphabet. And similarly, if we look at the output contacts, the output contact label B is now next to the A contact on the outputs. The output C from the rotor is next to the B contact, and so on. So if you imagine following through a signal here, like if we had a signal which entered at A, so if this rotor was in the fast position and we typed in A, that now goes not to E, but instead it enters the rotor at B, follows the path for B like this up to G, and then it enters, then it connects to the F contact right here to the F output contact. So we can describe this algebraically by using the alphabet cycle permutation that I've called P here. So this is the cycle which sends A to B, B to C, C to D, and so on. And then when it gets to Z, it gets sent back to A. So if we describe the resulting permutation, the new permutation after the rotation I hate this so much. I don't know why it looks like this now. So the new permutation oh God, it looks so bad. The new permutation, what is it? We have, first we shift one up through the alphabet, so we do P. Next we do the rotor permutation, so the neutral position rotor permutation, which is M, and then we shift down through the alphabet, so we can describe that as P to the -1. Okay, right. So in fact, we can generalize this to what happens when the rotor rotates by not just one step, but by any number of steps. So after I rotations, so after the rotor has moved through I steps of 1/26 of a turn, what we would have is the permutation p to the minus I m p. Okay, so there's one more calculation, one more complication about rotors that I need to describe, which is that every rotor has an adjustable ring setting or Ringstellung. So for obvious reasons, a lot of the rotor terminology is in German. And what the ring setting allows you to do effectively is to rotate the rotor wiring while leaving the alphabet tire in the same position. So that means even though the window position might be A, for example, by changing the ring setting, you can arrange so that the rotor performs the permutation that it would have performed if the window position was something different. And that means you can't tell what permutation a rotor is doing, even if you know what the rotor is, just by looking at its window position, because you need to know the ring setting as well. So we're going to adopt the following convention for describing the effect of the ring setting on the permutation performed by a rotor. The ring setting will be a number between 0 and 25, and if we have a rotor whose neutral position permutation is m, and if its ring setting is j, that's a number between 0 and 25, and its window setting is I, and we'll identify then the letters A to Z with the numbers from 0 to 25, then the ring setting, the overall permutation will then be p to the j minus I m p to the I minus j. Okay. So you might wonder why the ring setting is acting in the opposite direction to the window setting. It's just a useful convention, and it matches up with the convention used in a particular Enigma simulator, which I like, and which I will link you to later on in this video series. Okay, so in summary, every rotor has a ring setting. You can adjust the ring setting to be anywhere between, it's a number between 0 and 25, and the effect of that ring setting is to cause the rotor to do a permutation, to cause the permutation to implement the permutation that it would do if it were rotated to a different position. All right, one more. Okay, one last problem, which is turnovers. So we have already discussed how the right hand or the fast rotor rotates. So it rotates 1/26 of a full term every time a key is pressed. But I've not talked about how the other rotors move. And now I'm going to try and explain a little bit about that. So what happens is that every rotor has one more special feature, which is has a special window position called its turnover position. And when that position appears, if the rotor is in the fast position, then when this particular turnover position appears, it will cause the medium rotor to rotate by a single step. On the other hand, if the medium rotor's turnover position is in the window, then when the medium rotor rotates, it will cause the slow rotor to rotate forwards by 1/26 of a turn. So now you can see why the rotors have the names of fast, medium, and slow, because the fast rotor is rotating every single time a key is pressed. The medium rotor would rotate one step for every 26 characters, and the slow rotor would rotate once in every 26 squared characters. So that's why these rotors have their names. Okay, so let's look at, first of all, where these turnover positions are. So for the rotors conventionally known as 1, 2, and 3, the turnover positions are Q, E, and V. And what that means for rotor 1, for example, is that when the Q appears in the window and when that advances to an R, it causes the rotor to the left, if there is one, to advance by one step. All right, so let's do an example of this just to try and understand what's happening. So let's say we've configured the machine with rotor 3 in the slow rotor position, rotor 2 in the medium rotor, and rotor 1 as the fast rotor. So remember that the rotors were separate from the machine. You could take them out and move them around, and part of the way you configured it was by putting the rotors into the machine in a certain order. So let's say we've configured it like that, and that the window positions, to begin our example, were that the slow rotor was showing A through the window, the medium rotor was showing an A, and the fast rotor was showing AP. Okay, so after you press the key once, the fast rotor would advance from P to Q. Okay, actually I think I would like a different color. Let's undo that. Why can't I undo that? There we go. Okay, I want a nicer color. So after one step, the fast rotor now shows Q in the window, and the medium rotor still shows A, and the slow rotor still shows A. Okay, next time we press a key, the fast rotor will advance to an R, and that will cause a turnover in the medium rotor. So the medium rotor will now advance one step so that its window position is now a B. On the other hand, changing A to B in the medium rotor doesn't cause a turnover in the next rotor. You can see that the medium rotor is rotor 2, turnover position is E. That means when it goes from E to F, then that rotor would cause the next rotor to rotate. And so in this case, it will just stay as ABR. Okay, next step, we type another letter. The fast rotor will now go to S. But again, no turnovers on either the slow or the medium rotors. So they stay with their window position being A and B. Okay, so that's it. That's how the rotors. That's how the rotors change, and that's how they get their names of slow, medium, and fast. So this behavior would continue as long as we kept typing letters. Now, there are certain circumstances when it can be worse than this. Right? It can always be worse. It can always be more complicated, and it often is. There are certain circumstances which can result in a double turnover of the middle rotor. So that is, it can turn over twice in consecutive steps. That happens if it gets pushed into its own turnover position. You can see some examples in the second YouTube link at the bottom of the page there, which you can find in the clickable links in the video description, or in the double stepping paper which I've linked. So you can see all the gory details of exactly when you can have this unfortunate double turnover behavior in the links at the bottom there. Okay, and the first YouTube link there is a really nice 3D visualization of what happens in the machine when the rotors rotate. It's really good. I recommend that if you want to see some nice pictures of what happens inside the machine. Okay, next slide. Right. So final slide then, we got to talk about key exchange. So when you want to transmit encrypted messages, like before the invention of public key cryptography, which this is, you needed the sender and the receiver of the message to have some kind of shared secret, or as it's called, a cryptographic key, which they can use for encryption and decryption, and which is difficult for an unauthorized third party who's listening to the encrypted messages to recover. So in the case of Enigma, the shared secret is the machine state. And as we've seen, this consists of 4 different elements. Right? The configurable aspects of the machine were, first of all, the plug board connections. So as a machine user, you had a number of plugs, some varying number of plugs, and you could use them to connect some collection of pairs of letters on the plug board. Okay, next part of the machine state was the rotors in the machine and the order in which they appeared. So the Enigma had a number of different rotors. The actual rotors in use varied throughout the course of the use of the Enigma machine. And those rotors, whichever ones you chose, could go into the machine in any order. So you could choose any rotor for your fast rotor, a different rotor for your medium, and a different rotor for your slow rotor. Okay, so thirdly, the rotors themselves had ring settings. Each rotor had its own individual ring setting. And finally, the rotors could be configured so that a different letter was showing in the window. You could configure the window positions once the rotors were in the machine so that a particular letter was showing in the window. So in the context in which Enigma was actually used, senders and receivers agreed this machine state, agreed this secret key by using a key sheet, which was a piece of paper listing machine configurations which were to be used at particular times and dates. And this key sheet would, for logistical reasons, be shared by quite a large network of message senders and receivers. So there's an example of a key sheet on the right here. This is a public domain photo taken by someone in the US government. It shows a key sheet for the German Air Force Enigma quite late on in the war. But you can see here we have got the wheels here. So this part of the key sheet, well, let's go from left to right. I mean, right on the left here, you've got a number here. That's actually the day of the month. That's telling you that in this particular month, this row is telling you what settings to be used were on the 31st day of the month. You might wonder why it starts with 31 and goes down to 1. The reason is that I believe you were supposed to cut off the settings as they were used and then throw them away. So if that's going to make sense, you better have number 1 at the bottom so that you don't throw away the headings and then accidentally forget what all of these weird numbers and things were supposed to mean. Okay, so you've got the date in that first column there. Then you have which wheel goes in which position. So this is telling you should put wheel 1, rotor 1, then rotor 5, then rotor 3 into the machine in that order. Okay, next the key sheet has a column specifying the Ringstellung, the ring settings. So this says you should configure rotor 1 with ring setting 14, rotor 2 with ring setting 9, rotor 3 with ring setting 24. Okay, next bit, ignore this. It doesn't apply to our Enigma machine. It's just to a more complicated later version that was used by the Luftwaffe quite late in the Second World War. And next you have some plugboard settings. So we have at this point they were using 10 different plugboard connections, so 10 pairs of letters swapped in pairs, SZ, GT, DV, KU, and so on. So earlier on, there might have been a variable number of plugboard connections. There might have been a lot fewer plugboard connections used, but at this stage in the war, they were using 10 plugboard connections. This was actually a much better idea from a cryptographical point of view. Okay, last column, Kengruppen, ignore these, they're not relevant. Okay, so one last thing to say about the Enigma, which is the fact that the key sheet was in use by a large network of senders and receivers causes a problem because if everybody used the exact same machine configuration for their messages, then that would mean that every message was encrypted using exactly the same method. Cryptographers have a term for that. Messages which have been encrypted using the exact same method, so in our case, the exact same machine configuration, are said to be in depth. Cryptographers hate this. They hate messages being in depth because it leads to serious weaknesses in their cipher. You had to avoid this if you wanted your ciphers to be secure. So that means the key sheets cannot have been the end of the story when it came to how the machine was actually configured when messages were encrypted and transmitters. So for this reason, what tended to happen was the key material would specify part or all of the machine state, but each message would actually be encrypted using a slightly different message key chosen by the sender and somehow communicated to the receiver. So to begin with, at least, this differed only from the key sheet settings by its initial window positions, And there were various different message protocols for communicating what this message key was to the receiver. Some of those were very poor, others were better. We'll go into the specifics in future videos. For now, that's it. If you've got any questions, stick them in the comments, and don't forget to like and subscribe.